Welcome to Paradise Podcast number 106, and today we're talking about temperature-sensitive paint and how to use it to determine where the boundary layer transition is on airfoils and just plates in general in aerodynamics. And to do that, we're going to be looking at a paper called Boundary Layer Transition Prediction on Planar Turbine Cascade using temperature-sensitive paint and numerical simulation. So this paper looks at an actual physical experiment with temperature-sensitive paint and then numerical simulations to determine how accurate this prediction was, at least how closely related the two results are. So what is temperature-sensitive paint to begin with, and how does that differ to pressure-sensitive paint? So you've probably heard of pressure-sensitive paint because it's been around for probably about 20 years, maybe longer. And this is where you literally paint a surface with a particular type of paint that changes color under different pressures. So this is very useful because it means that you get a huge amount of data, and it's really dependent on the number of pixels you have on your camera, because each little part of the airfoil or whatever surface you have will change based on the pressure, and you can just take a picture of that and then process it and determine what the pressure is on this surface. Temperature sensitive paint is very similar, except you use temperature differences instead of, or at least heat transfer differences compared to pressure. So that shows slightly different information there. But again, it shows you so much information, and that's why and it's also non-intrusive, which is a very beneficial thing. So non-intrusive means that you're ideally not changing the flow at all. So for example, if you were to use hot wire, which is where you stick literally a probe inside the flow, then that's going to have an effect on the flow. That's intrusive, whereas pressure-sensitive paint or temperature-sensitive paint are not intrusive because they're not sticking anything into the flow. We'll get into more about how to set that up. So this podcast will be about temperature-sensitive paint and their effects and how to set it up properly. And this is an open access paper, so you can find it in the link in the description. So let's get on with the paper. So the complex flow field structure and loss mechanisms of cascades have become important research to improve the performance of aero engines. So cascades are just pretty much any time you have a bunch of airfoils working together. So they're usually aligned in a certain fashion to produce a greater effect than just each individual airfoil. So for example, a compressor or a turbine, that is effectively a cascade, and an aero engine is just a aircraft engine. So it's like a turbojet or a turbofan or a turboprop or whatever. So the state of the boundary layer on the cascade surface and the transitional location are an important basis for describing the flow mechanism of the cascade and analyzing its performance. Although the basic theory and occurrence mechanism of boundary layer transition are still under research and development, its importance in engineering practices has become increasingly prominent and has received extensive and sustained attention. For example, the transitional location and development process have significant impact on the lift to drag characteristics, boundary layer separation, and surface aerodynamic heating of the aircraft and aerospace engineering. So that's all true. In recent years, scholars have carried out a lot of work on flow display technology and measurement methods. So for example, a bunch of researchers use the hot film technique to measure the flow separation and transition on the airfoil surface. So hot film is very similar to hot wire, except it's just a little bit thicker. It's like a film instead of a wire, as the name would suggest. One major difference, I should actually stress that the benefits, the advantages and disadvantages of hot wires and hot films have sort of become blurred recently. Traditionally, hot films are significantly stronger than hot wires. They also traditionally had higher frequency responses. However, both of them have really high responses anyway, like tens of thousands of hertz are very common. You can get up to hundreds of thousands quite easily. However, in recent times, there have been a lot of advances in terms of hot wire and hot film technologies. So the differences between them aren't that great. For example, Dantec, they make hot wires which are very thick now, and that means that they're much stronger. So that advantage that hot films once had is no longer there. With these hot wires, though, their frequency responses dropped, but their strength is there. So as I mentioned, the differences between them are kind of becoming blurred as we progress. So other researchers also used hot film technology to detect the boundary layer state of compressor blades. And one way to do this is just by looking at the turbulence spectrum of the boundary layer, which hot films and hot wires are ideally suited to because of their high frequency response. So let's move on to pressure-sensitive paint. So pressure-sensitive paint, or PSP, is a well-established optical pressure measurement technique that can provide qualitative and quantitative surface pressure distributions on models with high spectral resolutions, as I mentioned. Temperature-sensitive paint, or TSP, is used as a similar optical measurement technology to PSP, but it is relatively rarely used in boundary layer transitions of the cascade. So this paper combines the TSP, or temperature-sensitive paint, wind tunnel test, and CFD to carry out predictive research on the boundary layer transition of a cascade. First, a TSP measurement method for the boundary layer transition of the cascade was constructed through the TSP technique and wind tunnel testing devices. Second, the wind tunnel test of the transonic planar cascade turbine was carried out under different inflow conditions, and the transitional location was obtained. Lastly, the boundary layer transition location was verified by comparing the numerical calculations to the results. So this is a little bit like you're sort of juggling things around. So you usually would use experimental results to validate CFD. In this case, they're doing the exact opposite. So how accurate will the validation be? It may not be 100% accurate, but you'll still get a good idea as to how accurate TSP is. So it may be within a few percent or 5% because the CFD is not properly validated, but that's still a good starting point for validating TSP usage. So let's talk about the temperature-sensitive paint principle. So the TSP technique is a modern optical measurement technique for the measurement of the temperature surface field distribution, and its basic principle is the thermal quenching of TSP fluorescent probe molecules. So what does that mean? So what they do is they paint a surface with this particular paint, and depending on how quickly it cools, that will determine how much light is given off. That's what this sentence means. So TSP uses luminescent molecules as probes that are mixed into suitable polymer coatings and coated on the surface of the aerodynamic models. That's the paint. Luminescent molecules are sensitive to temperature, and the luminescent quantum efficiency decreases with increasing temperature. So what that means is, as you increase the temperature, fewer photons are emitted. So we'll explain how this works later on, but that's just generally the principle. So depending on how many photons you are getting off of this surface, you can determine what the temperature is. So, or the intensity of light also is what this is known as. However, the heat transfer coefficients of the laminar boundary layer and the turbulent boundary layers are different. I won't tell you exactly how yet, but we'll get into it. So this results in the difference in temperature distributions in the laminar and turbulent regions. So to determine where the transition is, you can just look at how the temperature has changed, and then you can see, okay, that line there is where we've transitioned to turbulence instead of laminar, or we can see like, okay, this kind of region is where we are transitioning, and then finally we're getting into turbulence. And we'll see some pretty cool pictures later. So in this study, the technique was used to spray TSP on the surface of a cascade. So in table 1, the specific parameters are shown. So laminar and turbulent flows show different luminescent characteristics when the light source illuminated on the model is present. The light sources were 2 sets of 400 nanometer LEDs that were arranged on both sides of the camera. A 400 nanometer LED light was used to illuminate the surface of the model sprayed with TSP. At the time, the TSP was excited by the excitation light and emitted red light with a peak wavelength of around 610 nanometers. Then a CCD camera was used, and a 580 nanometer high-pass filter was installed in front of the camera to eliminate the influence of the excitation light and collect TSP luminous intensity images under different working conditions. So let's explain this. So what they did was they have their cascade, their airfoil, or whatever surface that you want. You paint it with this TSP, then you have to excite it with this light. And the only reason why you need to do that is because you need to excite it to give it energy so that the electrons will then move enough to then re-emit electrons or photons, back out, and that's the light that you want to see. In this particular case, they're using a 400 nanometer LED light, and they're shining onto the surface. Then this excites the electrons, and then they will emit a 610 nanometer light out. And depending on the temperature, that light will be brighter or less bright. And to get rid of this 400 nanometer LED light from corrupting the results, that was the excitation light. If we want to see the resulting light, we have to use a high-pass filter, so a filter that will block out anything lower than 580 nanometers. So we can just get the stuff that the cascade is now re-emitting. Those are the results we want. So the relationship between the light intensity and the temperature can be described by the Arrhenius formula. So this is in equation 1 here, and it's really simple. Using the above collected temperature and light intensity data, the TSP calibration data were fitted on the basis of equation 1 to obtain the relationship curve between the intensity divided by the reference intensity and the temperature under different pressure conditions. The calibration curve is shown in figure 1, so we'll go through this briefly. So as I mentioned, the equation they use to determine the temperature is very simple. So first of all, we need to have a reference illumination or a reference intensity level. You then need to have a reference temperature level that was taken at. You then have to have the illumination of, or the intensity of your object now. From there, you can then just calculate the temperature very easily just through, it's the I, which is the intensity you've measured, divided by the reference intensity, times by the temperature intensity, and then you get T out. It's very easy, or the temperature out. Some things about the TSP. First of all, it's not sensitive to pressure at all. So if you change the pressure by 10 kilopascals or a kilopascal, whatever, the change in the intensity does not change, which is pretty amazing. Secondly, the operating range for the pressures is huge. It goes from 1 kilopascal to 10 megapascals. Another important aspect, it can be used between 10 degrees Celsius and 80 degrees Celsius. Also, the response time is 0.75 seconds. So that's pretty quick when you think about it. I mean, the paint is changing intensity effectively sooner than, or like more frequently than every second. That's really good. The temperature sensitivity is 1.4% per degree Celsius. And the excitation wavelength can range between 400 nanometers to 550 nanometers. And the emission wavelength goes from 600 nanometers to 750 nanometers. Interesting thing here, the photodegradation rate is 1% per hour. So that means that the amount of intensity you get out will reduce by 1% every hour under the same conditions. So as long as you do your experiments very quickly, then you won't have a problem there. And as I mentioned in figure 1, they have a calibration curve which relates the temperature to the intensity of light, and it's linear. It's really nice. So if you know just literally 2 points, you can calculate the entire curve, and then any time you want to figure out what the temperature is, you just go to that linear curve. It's very good. So moving on, the wind tunnel test device. So in figure 2, they have a picture of this cascade, and it's just a bunch of airfoils lined up above each other, and they're kind of like shutters almost, where they're pointed down a little bit. The TSP transitional test was carried out in the turbine cascade test section of the variable density planar cascade wind tunnel. So that's just the wind tunnel there. The cascade model was placed in the wind tunnel test section. The camera and excitation light source were integrated into a specifically designed collection box and installed above the back of the test section. This study takes the transonic VKI-RG turbine blade as the research object, as shown in figure 2b, and the cascade consists of 7 blades. Now I should note that only 1 blade was painted with this TSP, the third blade from the top. So the transonic VKI-RG, I'm not exactly sure what that is, but I'm pretty sure VKI stands for Von Karman Institute, so maybe it's a particular cascade that the Von Karman Institute had developed or not. If you know more about this, let me know in the comments below, but this is just a particular type of cascade, I think. So looking at figure 3, they have a picture of the blade, or the blade that they painted, and the paint on it. So the observation blade is a non-metallic model produced out of epoxy resin, and the blade surface was sprayed with temperature-sensitive paint. The specific operation was to first clean the surface of the blade with alcohol and then spray the primer onto the surface. In order to prevent the induced transition from occurring in advance due to large particles on the surface was polished with fine sandpaper after the primer had been completely dried and cured, and a luminous top coat was applied. So let's talk about this, because this is very important. So I've talked about surface roughness before, and I'm going to actually do a few podcasts coming up about how surface roughness affects the flow over airfoils in particular. But it does make a big difference. So if you have a rougher surface, you will get a very different boundary layer transition point to if you have a very smooth surface. So if you have an object and you want to be able to compare it to other objects, you should really try to control the surface roughness. Reynolds number is not enough, and nor is the Thomas tensor. You need to have the surface roughness as well. So in this particular case, when you paint an object, speaking from experience, when you paint like an airfoil or something, often it gets quite rough. And that is due to a few factors, including just dust in the air settling on the surface. So you get a bit of roughness there as it's drying. So a good practice is to sand it. And you can use different grade sandpaper, so different grits, so like 40, 80, up to, 2000 or something, to get it really smooth. And that's what they're doing here. They're sanding it down to make it very smooth so that you won't have this surface roughness changing the boundary layer very artificially. And this is important when we come to CFD, because when we do CFD, we often don't take into account the roughness of a surface. So the smoother the surface, usually the better in terms, well, this is a tricky point because if you're using a RANS model, the Turbulence model you use, they are based on empirical data, the different coefficients that you use. So they're really just based on average surface roughnesses in the end. So you want to have effectively an average surface roughness, which is kind of like a machine finish, which is usually smoother than a painted surface. So you do want to smooth it to some extent with sandpaper, and that's what they're doing here. So schematic 3A shows the coating surface structure. So you have the blade surface, then the primer, then the top coat, which is that TSP effectively. Also in figure 3B, we have a picture of the airfoil cross-section, and it's a very cascade-like airfoil, like a cross-section. It's quintessential. So to give you an idea of what it looks like, think of like a hockey stick, but then you squash that corner a lot to make it more rounded, and that's very much what it looks like. It's a very cambered airfoil. It's fairly thick, and yeah, it's at like a 30-degree angle of attack. So it's very extreme. So in moving on to some of the results now. So in figure 4, we're going to be looking at the validation of this data now to see if the TSP actually does what it was supposed to do. So the TSP measurement results at different outlet Mach numbers and inlet Reynolds numbers are shown in figure 4. Due to the difference in the heat transfer coefficients of laminar and turbulent flows, there was a significant temperature difference between these two sections. The slight unevenness of the temperature-sensitive paint spraying on the blade surface and the airflow on the blade may have mixed the tiny particles hitting the blade surface and causing the transition to occur earlier, resulting in a sharp temperature distribution, but the temperature ratio, so the temperature divided by the reference temperature, distribution on the suction surface changed significantly as a whole, and the occurrence of the transition could be determined then. So in other words, due to variability in the flow and the coating on the surface, the intensity was not uniform in the regions where it should have been uniform. There were some slight variations. However, these variations were very small compared to the major variations between the turbulent and laminar regions. So even though you do get these small variations, overall you can actually see the difference quite clearly between the laminar and turbulent boundary layer sections. So that makes it very easy to find where this transition point occurs. That's what this means. So the transitional location was about 0.63 lakhs. So that's 0.63, sorry, 63% of the chord, and a Mach number of 0.4. This is shown in figure 4A. When the Mach number increased to 1.03, so now we're above the speed of sound, and especially on this airfoil, because it is so curved, we are definitely above the critical Mach number. The boundary layer transition occurred at only 0.42 lakhs, so 42% of the chord, so it moved upstream by 21%, so a lot towards the leading edge. When the Reynolds number was decreased, as shown in figure 4C, the transition point moved backwards to 47% of the chord, so that makes sense. And then compared with figure 4B, the transition location shifted back for this Mach number, and this was at 0.49. Then they had a different Mach number, so they increased the Mach number again to 1.2, and they found that but the Reynolds number was not that much higher. They found that the boundary layer transition point only moved back slightly. So there's a fourth situation here where, under certain conditions, with the shock wave, the boundary layer transition point did not behave predictably. It went back instead of forwards. Now, we're not going to go into why that is here. In the next podcast, we'll go into more about this kind of thing. But in this podcast, we're just going to look at how the temperature-sensitive paint is working. So what we found here is if you increase the Mach number up to a certain point, the transition point will go towards the leading edge. Once you go past a certain point, so 1.2 Mach number in this case, it actually goes back a little bit. So finally, we're going to look at whether this temperature-sensitive paint method was good or not. So we've found some results, generally speaking, but we're now going to use CFD to validate it better. So in figure 5, they use a geometric model of the transonic VKI-RG cascade, which is the same as the wind tunnel test model. Since transitional calculations had a high requirement for the mesh refinement of the normal and tangential directions near the wall, The total number of subsequent meshes increased sharply, and the requirements for computing resources were further increased. In other words, because refining this mesh became prohibitively expensive, they only stuck with a certain number of cells, which was 8 million in total. So they instead of modeling the entire cascade, so all 7 blades, they're only modeling one because of this prohibitive number of cells. So the model was like the geometry was effectively like a big rectangular box. The blade was 3 chords downstream from the inlet and 8 chords from the outlet. So it's a little bit restrictive, but still it's not too bad. Then in the span-wise direction, they had 120 nodes. In the stream-wise direction over the airfoil, they had 240 nodes. So it's a fairly well resolved airfoil. Let's talk about the setup. So in figure 6, they say all numerical simulations adopted 3-dimensional compressible RANS equations. The transition model was the gamma theta model, which was based on the SST K omega model. So the gamma theta SST is quite similar to the SST K omega model, which I've gone on about at length in podcasts about how good it is. In my experience, gamma theta is not as good as K omega, but it is still very good. So they're just opting for that. Perhaps they've found better results for this particular situation. I'm not sure. But that's quite a good model still for RANS. It's far better than most other turbulence models. So they're saying that they picked the gamma theta SST model, which considers the natural bypass and separation bubble transitions and can more accurately predict the transition location. So let's talk about these different transition mechanisms. So they said natural transition, and this is natural transition is like where you have like little waves that break down 3-dimensionally and they just transition straight to turbulence. So this is a fairly low turbulence intensity level transition path, and it's fairly hard to predict. Bypass transition is far easier. So this is where you have a very big disturbance and it just transitions instantly to that point, to transition to turbulence there. So that's much easier to model. Then we have the separation bubble transition, which in my experience is the hardest out of the 3 to model. This is where you have, I've done podcasts on this, but this is where you have flow going over the airfoil or any surface, and it's laminar. Then it separates, then it reattaches, and by the time it reattaches, it's turbulent now. And in this point where it detaches to reattaches, you have this circulation bubble, this recirculation dead zone. And this effectively increases the camber of whatever you're using, and it can increase the lift coefficient dramatically. There are some benefits to it and some detriments. I've covered in another podcast, I won't go through here, but that's that transition path. So trying to figure out what path your boundary layer is taking is very difficult with the RANS simulations, which is why you need to have a very good turbulence model. I've mentioned that the SST K omega model can handle this stuff very well, but the SST gamma theta model can also handle that quite well. In my experience, the gamma theta model cannot handle the separation bubble as well as the K omega, but maybe in this particular case, they're looking at other transition paths more in depth. So maybe that's more suited there. I'm not sure. So let's move on here. We've talked about the RANS models and the CFD setup. Now let's talk about figure 8, which is a comparison of the isentropic Mach number on the blade surface. So the reliability of the numerical model was verified by comparing the experimental results of the isentropic Mach number and the transitional location of the blade surface. Figure 8 shows the isentropic Mach number distribution on the surface at 50% of the blade height when the angle of attack was 0 and the outlet Mach number was 0.78. Overall, the numerical results of the isentropic Mach number, is in good agreement with experimental results. So looking at the Mach number over the surface of the airfoil. So they're looking at, let's say, 10% down, 10% of the chord downstream of the leading edge, then 20%, 30%, 40%, and seeing what the Mach number is at this point. Because as I've mentioned in other podcasts, as the flow goes over an airfoil, it accelerates in velocity. That then increases not only the velocity, but also the relative Mach number. And you can figure what that is out, and then you can also plot it compared to CFD and see if your CFD is performing well. In this case, it's very accurate. So they have their Mach number distribution over their airfoil, and it matches experiments very nicely. So we can say that this CFD is quite well validated. So that means we can trust it. So now that the CFD is validated and we have experimental data for this temperature-sensitive paint, let's compare the two. In Figure 9, we do just that. Figure 9 is a comparison of the transitional location between the simulations and experiments. And the transitions locations were basically the same at about 42% downstream. So let's talk about this figure quite a bit more because there is some stuff to talk about. So in the bottom part, like the figure 9b, that is the CFD results. Figure 9a is the experimental results. And in figure 9a, you can see that there is a lot more variation to the intensity of light coming off of the airfoil, whereas figure B, it's much more uniform. That is to be expected because figure 9a, that has some variation in the thickness of the temperature, as well as potentially the number of photons in like a certain area, number of luminescent molecules in certain areas, but also maybe surface roughness, etc. So there will be some differences in the illumination, whereas in figure 9b, the intensity is going to be very independent of these parameters because they're not actually taken into account in CFD. Like CFD is much more uniform. In experiments, we do have these variations for temperature-sensitive paint. However, despite these slight differences, the general overall results are very similar. So we can see that for 9b, the point at which the boundary transitions is at 42% of the core downstream, and it's very clear. We go from like this very dark blue point to a aqua point very sharply. In figure 9a, we also get a very sharp change. We go from like being a blue-green to being an orange-red very sharply. Again, there is some variation, but that's due to the application of the paint, which is to be expected. So we can say that the CFD is quite well validated. Not only does it predict the Mach distribution over the Mach number distribution over the airfoil, but also it predicts the boundary layer separation or transition, much more accurately than I even expected, based on potential difficulties of this CFD and differences in the CFD setup. So it is still quite well validated. It's giving quite good results. So that means that TSP, or temperature-sensitive paint, can quite accurately tell us where the transition point is along an airfoil or any surface. In the next podcast, we're going to be going through how the Mach number and how the angle of attack and how the shockwave influence affects these different transition points. And we're going to be using CFD for that. That's going to go past TSP into a different topic. So that's in this podcast. We've covered that TSP is a very good way of, if you apply it properly, a very good way of determining where the transition point is in a laminar to turbulent boundary layer. And we've looked at some CFD to do that as well, to validate that. So if you like this, make sure to like, subscribe, and check out our other podcasts as well, like, for example, the laminar separation bubble podcasts, or the transition and surface roughness podcasts and turbulent intensity podcasts. And if you want to get better at CFD and theory yourself, check out our courses in link in the description. And if you want to get better at or have better CFD validation data and better experimental data, check out our Atmosphere Hawk. The Atmosphere Hawk increases the accuracy of your results by 2 to 4% in your experiments. And this is very important because if you use, if you're doing experiments, even just for CFD validation, you're going to have a 2 to 4% error in that validation data, which will make your CFD validation much more difficult and probably more erroneous in the long run. So our Atmosphere Hawk accurately measures the density of air for you, which is the major cause of this 2 to 4% error, which most people do not accurately measure or measure at all. And that means that their CFD validation data and the experimental data is wrong effectively. So get the Atmosphere Hawk, it makes your life much easier and your data much more accurate and trustworthy. Link in the description, and I'll see you next podcast. Peace out, amigos.